Take a look at this polar bear. Cute, right? Now take a closer look. This polar bear is not happy. Its habitat has been destroyed, and it's all because of global warming. Global warming is a phenomenon that's caused by increased concentration of pollutants such as carbon dioxide and CFCs. A lot of the electricity that we use today is made by burning fossil fuels. These fossil fuels go into the air and trap sunlight, warming the atmosphere. Now, you've probably heard of this, and you've also probably heard of the ways that we can solve this, using renewable energy. Solar power in particular is probably the best way that we can combat global warming. But it's not realistic for everyone to be using solar power because solar panels are expensive. Fortunately, there are these materials called perovskites that can help. Perovskites have shown great potential in the field of photovoltaics. The perovskite mineral is very common in the Earth's crust, and it has potential in increasing the efficiency as well as reducing the cost of solar power. Perovskites have a general formula of AbX3, where A is a cation, B is a divalent metal, and X is a halide. There are also these materials called halide double perovskites, which are made by combining mono and trivalent cations. Perovskites are usually made out of lead, an example of which is the methylammonium lead halides. But lead is dangerous. It's a harmful toxin. And the solar panels that have been made out of perovskites have low shelf life, so researchers are looking to find alternatives for the composition of these perovskites. Now look at this through the lens of a researcher for a bit. You've done all the experimentation that needs to be done, and you've also received data from other scientists. Compiling everything, you have a huge data table. It has thousands and thousands of entries from all the possible halide perovskite compounds. So how are you going to read this table? How are you going to analyze it? Well, it turns out that you can actually use certain artificial intelligence algorithms in order to analyze the data that you have. These algorithms are all just based off of these things called decision trees. Decision trees are what they sound like. They're literally trees that make decisions. Decision trees have three main components: root nodes, internal nodes, and leaf nodes. Nodes are just the boxes that you see on a decision tree. Let's start with the root node. The root node is the node that's on the top of the tree. It has arrows pointing away from it, but none pointing towards it. The root node is usually the parameter that classifies the data the best. The next type of node is an internal node. Internal nodes have arrows pointing towards and away from them. They're also just called nodes. And finally, leaf nodes. Leaf nodes are what you get at the end of the tree. They give you either a recommendation or a classification. And they have arrows pointing towards them, but not away from them. Your decision tree is most likely not going to be completely accurate. No leaf node can 100% accurately classify the results. And that's why we call these nodes impure. Now, this makes sense intuitively, but how do we quantify this? How do we measure the impurity of a node? One popular way of doing this is Gini impurity. This method was named after Italian statistician Corrado Gini. Gini impurity is equal to 1 minus the probability of yes squared minus the probability of no squared. The less impure a node is, the better it is at classifying samples, and the root node is typically the parameter with the least Gini impurity. By calculating the Gini impurities of all the parameters, we can make the optimal decision tree. But a singular decision tree isn't very accurate, and that's why we use random forest to help us. In order to create a random forest, we first have to create a bootstrap dataset. What this is basically a new dataset made from random entries from the original dataset. And repetition is allowed. We would then create a decision tree out of the new dataset. But if we just stopped here, we'd have the same problems with accuracy. So we repeat this process hundreds of times and get hundreds of decision trees. Now, instead of receiving input from one tree, we can receive input from all the trees in the forest. If we were given a sample to classify, we would run down all of the trees and keep track of the results. By majority, we would eventually get a classification. The process that we use to classify the samples is called bagging, bootstrapping and then using the aggregate of the results from each decision tree to make a classification. Now, when we created the bootstrap dataset, we found random samples from the original dataset. Since repetition is allowed, we expect there to be data points that aren't in the new dataset that were in the old dataset. These data points comprise the out-of-the-bag dataset. So we can run all of the out-of-the-bag samples through all of the decision trees in order to see if we can get accurate results. One AI algorithm that's typically used for classification and optimization problems is AdaBoost. AdaBoost combines many weak learners, or stumps, in order to make accurate classifications. A stump is a decision tree with just a root node and 2 leaf nodes. There are 3 main principles to AdaBoost. AdaBoost combines many weak learners, or stumps, in order to make classifications. Some stumps get more say in the final classification than others. And each stump is made based on the errors that the previous stump made. Using this algorithm, we can find the optimal chemical formula for the perovskites and hopefully increase the shelf life. More specifically, we can calculate the decomposition energies, which can help us to gain insight in the thermodynamic stability of these compounds. We can also discover new compounds. In this way, we can make solar technology affordable for everyone and reduce global warming. And of course, we can help this polar bear to live happily. Thank you.